Assalamualaikum and hi everyone. We are from Group 1. We are doing experiment 3 minor losses in pipes. Okay. For the introduction, liquids only flow through pipes if forced to do so by pressure caused by a pump off by gravity. It is found that the pressure measured at any point in the pipe decreases in the direction of flow. This pressure loss is caused by friction in the liquid and between the liquid and the walls of the pipe. The fluid flow apparatus consists of a pump pushing water from a holding tank through a series of pipes and back into the tank to form a closed loop. The piping contains a number of valves that can be used to force the water to flow through any or all of the five sections shown, depending on which valves are open or closed. If all the valves are closed, no water will flow. This would damage some pumps, but not the centrifugal pump used in the lab. Okay, now for the objective, to determine the loss coefficient Kf and minor head loss Hf for various pipes and fittings. For the scopes, in this experiment, the minor energy losses from different sections of the pipe components, namely the Y type, the T type, suddenly enlargement section, sudden contraction section, and bends at 90 degrees and 45 degrees angles in pipe sections were calculated. The experiment results were used to calculate the loss coefficient and minor head loss.
For my part, I will talk about theory and working principles. In the piping system, different flow rates require to pass through a variety of fittings, bends, or abrupt changes in area. A1V1 meet the junction will produce A2V2 plus A3V3. So we can conclude that when the flow separated at the junction, minor head loss, which is the HLM, will form. Next, the Bernoulli equation between 2 points for the horizontal, which is the Z1 equals to Z2 pipe, the pressure loss and the total head loss, which is the HLT, can be determined as the equation below. So we want to find the total heat loss, which is the HLT. So as we know that P1 minus P2 over rho G equals to V2 square minus V1 square over 2G plus HLT. Then the HLT, we know that HLT we can find from P1 minus P2 over rho G plus V2 square minus V1 square over 2G. And we also can find HLT from the another equation, which is HL plus HLM. And HL is FL over DI times with the V square over 2G. And the HLM is KL times V square over 2G. So from here we can conclude that HLT is equals to P1 minus P2 over rho G plus V2 square minus V1 square over 2G, or FL over DI times with V square over 2G plus KL times V square over 2G. And the P1 minus P2 over rho G is equals to H1 minus H2 also. Next, we'll talk about the loss coefficient, which is the K. First part is the sudden expansion or enlargement and sudden contraction. The K for the sudden expansion and the contraction we'll get from the figure below, and the KL I will arrange from the equation 7 and equation 8. After rearrange these two equations, I will get the KL equals to 1 minus AI1 over AI2 square. So this is the second part, which is the elbows, pipe bends, and pipe branches. So for this part, the K I will get from the figure 2. Next, experimental setup. The experimental setup consists of inlet valve, 2-tube manometer tube, tested pipe section, and outlet valve. Then I will talk about the methodology. For the first step, switch on the main switch and pump. Secondly, fully open related valve for tested component in pipe section. And for our experiment, we will do about sudden enlargement and contraction, which we will open the V1 and V11. Then secondly, for the Y type, we will open V3, V8, V10, and V11. Then for the T type, we will open V3, V7, V10, and V11. Then for the angle 90 degree, bend 90 degree, and angle 45 degree, we will open the V5 and V11. Okay, then third step, wait for a while to remove any air bubbles for the tested pipe section. Then connect manometer tube to the inlet flow, which is the H1, and outlet flow H2. Fifth, record value H1, H2, volume water collected and time. So close the knife valve to collect water in the tank and use the stopwatch to record the time based on desired value. Then record 5 different values by reducing opening of outlet valve, which is the V11. Then, the manometer tubes were removed after finish to avoid the bubbles in the tube. Open related next valve for next tested components, which is the Y-type, T-type, and 90-degree bend and so on. Lastly, turn off the main switch.
My name is Nur Kamila and I will explain about the result. So for table 9.1, data for sudden enlargement and sudden contraction. Table 9.2, data for pipe branches. Table 9.3, data for elbow and pipe bends. Now for discussion, we need to calculate the minor head loss and the loss coefficient for each of the pipe component. So first, for sudden enlargement, the diameter for one eye is 0.017 meter and the cross-sectional area of the upstream A1I is 2.2698 times by 10 negative 4 meter square, and then find the D2I, which is 0.0284 meter, and the cross sectional area for the A2I is 6.3347 times by 10 power of negative 4, and then we need to find the kinematic viscosity by using the table of properties for water, and then lastly we will find the major losses and the loss coefficient, which is 0.4118. And then for sudden contraction, D1I is 0.0284 meter and the cross-sectional area is for A1I is 6.3347 times by 10 power of negative 4, and the diameter for D2I is 0.017 meter and the cross-sectional area A2I is 2.2698 times by 10 power of negative 4, and lastly we will find the loss coefficient which is 0.4118 and find the head loss for each of the flow rate. And for Y-type, we will find the DI, which is 0.017 meter and the cross-sectional area, which is 2.2698 times by 10 power of negative 4, and the loss coefficient, which is 2.0, and find the head loss for every flow rate. For T-type, we will find the D equal to 0.017 meter and the cross-sectional area 2.2698 times by 10 power of negative 4 meter square, and the KL is 2.0, and the head loss HLM for every flow rate we will calculate. Now for 2 times by 90 degree angle, we will find the diameter, the cross-sectional area, and the kinematic viscosity and the loss coefficient, which is 3.0. And lastly, we will do the table and calculate the minor head loss for each flow rate. For 2 times 90 degree bend, also same, we will find the diameter, the cross-sectional area, and the loss coefficient KL, which is 1.4, and lastly we will find the head loss for every flow rate. For 2 times 45 degree angle, we will find the diameter also, the cross-sectional area, and the loss coefficient KL, which is equal to 0.8. And we will do the table and find the Reynolds number, the minor head loss for every flow rate that we have. Now discuss the effect of different water flow rate, pipe diameter and pipe bends on the value of loss coefficient KL. So water flow rate, higher flow rate result in increased water velocity, which enhance turbulence and frictional losses. When the velocity rises, the flow may shift from laminar to turbulent, causing greater energy losses due to the chaotic and turbulent motion of the water, thereby increasing the KL value. So for pipe diameter, sudden enlargement has largest KL value than sudden contraction generally. This is because when the flow moves from smaller to a larger pipe, it expands abruptly, leading to significant turbulence and the formation of recirculation zones when the fluid is moving chaotically. This creates higher energy dissipation as the flow adjusts to the larger diameter. In contrast, in sudden contraction, although there is turbulence where the flow narrows, the fluid compresses and speeds up, which is less disruptive than the expansion in enlargement. The energy losses are more pronounced in sudden enlargement due to the greater disruption and adjustment required by the flow to stabilize in the larger pipe. So for the pipe bends, the 90 elbow has the highest KL value, followed by the 90 bend and the 45 degree elbow. Sharper bends result in a higher KL value because they cause a more abrupt change in direction, forcing the fluid to quickly adjust its flow path, which leads to increased turbulence, flow separation and friction against the pipe walls, thereby causing more energy dissipation. Smoother bends help minimize this disruption, reducing turbulence and frictions, and thus lower the KL value. The KL value for both Y-type and T-type branches is the same, likely due to similar geometric factors such as pipe diameter and thickness. However, in practice, the T-type branch tends to have a higher KL value compared to the Y-type, as the Y-type generally features smooth transition. And lastly, briefly discuss on factors contributing to error or inaccuracy in experiment data and the possible recommendation to improve the existing result. So the factor first is the presence of air bubbles in the pipes and tubes can cause pressure fluctuations, inaccurate velocity and flow rate measurements, and turbulence during water flow, all of which can affect the KL value and lead to minor head losses. Instability in water flow rate result in significant fluctuation in water level between the two tubes, making calibration difficult and impacting the value of H1 and H2. Parallax error may occur when reading the meniscus level of the water of the or the manometer, as the distance between the meniscus and the observer eyes can distort the readings. So the recommendation is thoroughly flush the system before use to remove any trapped air. Second, use a larger reservoir to help maintain a more stable water pressure and flow rate. And lastly, ensure that measurements are taken using a long ruler at eyes level with the meniscus to avoid parallax error.
So, to conclude this experiment, I've come up with a simple conclusion where the minor losses in piping system which arise from fittings such as elbows, teeth, and valves plays a significant role in overall head loss. And the objective of this experiment is achieved whereby the loss coefficient and minor head loss for different pipes and different fittings are determined. It can also be concluded that the loss coefficient in pipes is dependent on the flow rate of the fluid, diameter of the pipe, and the pipe ends. The value of KL will decrease when the internal diameter of pipe increases. The minor head loss is affected by the diameter of pipe when the fluid encounters a sudden enlargement or contraction, elbow at 90-degree angle and 45-degree angle. Based on the result, the data obtained deviates slightly from the theoretical value, which result in a significant value of percentage error. This may be due to some errors made while conducting the experiment. Hence, precaution steps should be taken to improve the accuracy of the result. Next, as for the safety procedure, you have to make sure do not touch the main switch with wet hand to avoid electric shock. Second, the two-tube manometer should be confirmed that no bubbles inside the tube before taking the reading. Third, ensure the rubber tube are connected firmly to valve. Fourth, place eyes position perpendicular to the scale of the manometer to improve the accuracy of the experimental data taken. Check the condition of the apparatus and pipes before starting the experiment. So this is the reference that we use to do our lab report. So that's all from us. Thank you.